Without a microphone, so please tell me if you can't hear me. Okay. So thank you very much for this kind invitation to give these lectures and your hospitality. It's a real honor to speak here in this lecture series. What I'm going to be talking about is representation theory and geometry. So some kind of basic theme is that if you look at a question in representation theory, it seems like it is a question in algebra. The statement is, for example, it might be, can we find certain matrices that multiply in certain ways? Or how many such matrices are there? Something like this. It's an algebraic problem. But what tends to happen is that often the deepest things that we know in the theory, we've first understood from geometry. And so it's a strange situation. You have a question that seems like it's a question in algebra, but its explanation first comes from geometry, and then you attempt to understand, perhaps in the language of algebra, why this is true, and then this leads you on to more questions and greater understanding. And so there's basically the first lecture today will be about representation theory, and then the second lecture will concentrate on geometry. Okay. And I also should say that this is essentially a kind of doubled version of the talk I gave at the ICM in Rio a few months ago. So let's see. So first I want to, so this is intended to be a very general audience talk. So I will not assume that you have any specific background in representation theory. So I'll first remind you what a representation is. So on the left we have an icosahedron, and we can look at the symmetries of this icosahedron as an abstract group. But in this particular case, the symmetries happen to be given by linear maps. And so in fact we have a concrete realization of the symmetries of this group as a set of matrices, as a set of 3 by 3 matrices over the real numbers. Okay? And this is an example of a representation. One very important thing to bear in mind is that in this particular case the representation is faithful. So we have a homomorphism from G, that's this abstract set of symmetries, into a group of matrices. And in this case this homomorphism is injective, but in general we want to consider all such maps, not necessarily injective maps. So for example, an important representation is the trivial representation, where we just take a one-dimensional vector space here and consider the map that sends every element of G to 1. Okay. So this is a concrete example here. So here I consider a triangle, and I've chosen my basis vectors in this nice way, and then I get 6 matrices that represent the symmetries of a triangle. Okay. So why do we study representations? I think that this is not an obvious thing to do. So first, to study groups is not an obvious thing to do, but Galois explained to us in about 1830 that this is a very, very good idea to study groups. But after Galois, you had many people studying the abstract structure of permutation groups. So for example, how can this group act on a particular set? But to ask how can a group act on a vector space is a slightly strange question initially. And I want to give you 2 examples that I think justify why this is such a good thing to do. So the first question, so if we take the symmetric group, the group of all permutations of n elements, we can consider the question of how does this group act on sets? Okay? So how can we realize Sn as a permutation group? And if we have such a set, so Sn, our group moves elements of the set around, and we can of course break our set up into transitive sets, where the Sn action is transitive. And now such a set is classified by a subgroup of our symmetric group up to conjugacy. And so these 2 questions here, Sn sets up to isomorphism and subgroups of Sn up to conjugation, are basically the same, but this question is extremely hard. So if you think any finite group is a subgroup of some symmetric group, so this is essentially writing down a list of all finite groups, which we are nowhere near doing. Okay, so this question is extremely hard. On the other hand, if we look at the theory of representations of the symmetric group, this was one of the first examples worked out in the theory. It's absolutely beautiful. You can do it reasonably easily, and it's universally useful. People use this in biology and computer science. It's everywhere. Okay? It's the first example. The second example is from arithmetic geometry. If I have some polynomials defining a variety over the rationals, so I have a certain set of polynomials with rational coefficients, and I would like to understand, for example, does this set of polynomials have a rational solution? So this is the question of Diophantine problems, and it's enormously difficult. We've been thinking about this question for hundreds of years. But enormous recent progress has been made by, there's various passages from a variety over Q to something called a Galois representation. So this is some kind of set this is like an object in the category of sets, whereas this is a linear object. And this passage is one of the most powerful tools in modern number theory. For example, Fermat's last theorem is proved by assuming you have a solution to Fermat's last to the Fermat equation, building some funny elliptic curve, studying the Galois representation that it would lead to, and then arguing that such a Galois representation cannot exist. Okay? So this is, I think, a really beautiful example, a historical example of why it is so non-obvious to study representations. So this is Burnside. He wrote the first English language book on group theory in 1897. And Cayley, who was another English mathematician, was emphasizing that, so in the work of Galois, it's not really clear to what extent Galois thought of a group as an explicit set of permutations, and to what extent he thought of it as an abstract thing with a composition. Okay? And Cayley was very much emphasizing that you should think of a group as we do today. A group is just a set with a composition. It's not permuting anything in particular. And this is what he's starting off to say. He's saying Cayley's dictum that a group is defined by more means of laws of combination of its symbols would imply that we shouldn't seek any more concrete mode of presentation than is absolutely necessary. This is what he's saying here. Okay? But then he spends an enormous amount of time studying the actions of groups on sets. And this is very interesting. So at the end, he says, it would be difficult to find a result that could be most directly obtained by consideration of groups of linear transformations. So here he's saying that representation theory is essentially useless. Okay? Basically. Yeah? So this is 1 year after people first started studying representations. So this is in the preface to the book. This is like the first page, basically, of the book. Representation theory is useless. Then, about, I think, 14 years later, he writes a second edition in 1912. Okay? And then he says, in the first book, in the first version, I didn't study representations. But now he says, he's gotten used to representation theory, and he says, in fact, it is now more true to say that for further advances in the abstract theory, one must look largely to the representation of a group as a group of linear transformations. Okay? And then he spends many chapters at the end of the book studying representation theory. So Burnside is a very, very famous good mathematician, and it took him some time to appreciate that representation theory is a good idea. Yeah? So let's consider the symmetric group. I want to go through a little bit the theory of simple representation. So let's consider the symmetric group acting by a permutation of coordinates on R3. So there's two invariant subspaces that are very natural, that kind of stare at us. The first one is that all coordinates are equal. This is obviously preserved by permuting coordinates. The other condition that's preserved by permuting coordinates is that the coordinates sum to 0. And so we can imagine our representation is broken up into two pieces. This trivial representation, this is where all the coordinates sum to 0. And actually, if you write down the matrices for this space, you get those 6 matrices that I wrote down before. And so this splits up this into two pieces. This is an example of something that happens all the time. So a representation is simple if we can't split it up in this way. And basically, the task is to find the simple representations. This is one of the basic tasks in representation theory. Okay? And a representation is semi-simple if it breaks up in this way as a direct sum of simple representations. So I just want to give you an example so that this is actually remarkable that this happens, that it splits nicely into two pieces. And I just want to give you an example to show that this is remarkable. So now we just change our field. So before we were working over the real numbers, now we change our field over to F3. And we have two invariant subspaces, as before. Nothing changes. But now something funny happens. If all my coordinates are equal here, I'm something like lambda, 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 then when I ask, does it belong to this subspace, the answer is yes, because 3 lambda is 0 times lambda is 0. So now it used to split as this plus this, but in this case now that's sitting inside it, and we get a filtration where each time the dimension grows by 1. So dimension 1, 2, 3. And so this is a picture of what this representation looks like. It has a trivial representation. The quotient is actually the sign of a permutation. Then we have the trivial representation. So if you would like an analogy to think about in representation theory, it's a little bit like the representations are just matter, all things in the universe. The simple representations are the elements, and semi-simplicity is the statement that the elements don't interact in any meaningful way. Okay? It's a very useful analogy to keep in mind. And what we're searching for is a classification. We'd like to know how many elements there are, something like a periodic table. And then we would like to know specific information. For example, what's the dimension of this representation, which is something like the mass of this element. Or we would like to know how certain elements act, etc. And so this is something like detailed information in the periodic table. So what I want to talk about in these two lectures is I want to talk about a number of topics in representation theory and then connect them to geometry. So the first example is MASCHKE'S theorem from 1897. This is exactly the same year as this Burnside quote that I gave you before. Compact Lie groups. So this is part of the semi-simple world. And then I want to go beyond the semi-simple world to the Janssen conjecture and KAZHDAN-LUSZTIG conjecture. Modular representations. So this is, again, mod P, like we just saw in this example of the symmetric group. And modular representations of symmetric groups. And this might look like... So I think that any pure mathematician recognizes these as important objects. Whereas these might seem like they are rather abstruse choices. But in fact, it's these examples that have given us amazing insight in the last 30 or 40 years in representation theory and have then been applied to other situations like non-compact Lie groups, p-adic groups, etc. So although this looks rather special, it's in fact very, 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 very important questions in representation theory. So I want you to keep the following pattern in mind. So there's some kind of connection between representation theory and geometry that we'll see examples of. And you can ask, what is geometry actually giving you in representation theory? And it turns out that often it's giving something like an invariant form, something like a symmetric form or a Hermitian form. So if you would like some kind of analogy to think about, you can think about, for example, an L2 space of functions might be a representation if a group acts, but it has this Hermitian form. Another example is if I take a cohomology ring, then it has an intersection form. So these forms are crucial, and sometimes you can kind of forget about geometry and just look at the form, and then this still gives you enough to work with. And another related feature of these lectures is kind of semi-simplicity. So semi-simplicity, this is the fact that elements don't interact, happens kind of way more than it a priori should. And that's very interesting. And I just want to, so I'll be dealing with real vector spaces and complex vector spaces and kind of jumping between them. And I don't want to say symmetric form or Hermitian form always. So I just want to say geometric structure. So a geometric structure is a symmetric form on a real vector space and a Hermitian form on a complex vector space. But an important point is that I don't assume that these are positive definite in general. So they'll be non-degenerate with some signature. Okay, so now we go to the semi-simple world. So this is MASCHKE'S theorem from 1897. Any representation of a finite group over R or C is semi-simple. So we saw one example of that. We wrote down a representation of S3 and saw that it was semi-simple. I want to explain the proof of this because, one, it's the first proof that you kind of ever see in representation theory. And secondly, it illustrates themes that just keep coming back. The first observation is that if V has a positive definite G-invariant geometric structure, then it's semi-simple. And the reason for that is rather simple. So if I have a sub-representation, then I can consider its complement, and I can split my vector space up by positive definiteness. But now, because of invariance, these are two, because this form is G-invariant, these two are sub-representations. And then I can keep splitting up, and then I get that my thing is a direct sum of simple representations. Yeah? And so the second observation is kind of more tricky. It's that we can just produce a G-invariant positive definite geometric structure. And the argument is averaging. So we take some positive definite structure and then we average it. And basically, because we've averaged, this is G-invariant, it's still positive definite. Because if we put in V and V here, we get a sum over positive things. And so we've got our G-invariant positive definite structure. And so this is the proof. Yeah? So what are the kind of themes here? So this is where we tried to show semi-simplicity, and we didn't kind of show it directly. What we said is that there's this additional structure. So this is semi-simplicity via introduction of geometric structure. And the second point, so there's something called Schur's lemma, which tells us that this geometric structure is in fact unique up to scalar. And so it's rather remarkable. Any irreducible representation has a unique geometric structure on it. It's kind of so if in this first slide I'd kind of chosen the wrong basis so that things were wonky, then I would do this averaging procedure and miraculously this would kind of make my triangle equilateral. So now we do the corresponding thing for compact Lie groups. So what Weyl noticed is that on a compact Lie group you can integrate. And so you can just do the same technique and you can produce an invariant positive definite geometric structure. And so he proved the following remarkable theorem. Any continuous representation of a compact Lie group is semi-simple. Okay. And again, we have this existence and essential uniqueness of geometry on our space. This is another beautiful historical event. So Élie Cartan was the expert in the algebraic theory of Lie algebras. And he had noticed this semi-simplicity for Lie algebras. But he couldn't prove it. And he tried very, very hard to prove it. And then Weyl proved this. He tried for about 10 years. Weyl proved this and sent Élie Cartan the manuscript in which he uses this integral over the compact Lie group, and he uses geometry to prove this theorem. And then Élie Cartan replies, the difficulty, I dare not say the impossibility, of finding a proof which does not leave the strictly infinitesimal domain shows the necessity of not sacrificing either point of view. And I love this quote because it's really saying we have to consider algebra and geometry on an equal footing. Yeah? And this is actually the real letter from the library in ETH in Zurich. So you can actually write to the librarian and they will send you a scanned copy of Élie Cartan writing to WEYL in 1925. And an amazing thing here is that actually Cartan was wrong in this case. So there is an algebraic proof, and it's not even difficult today. Okay? And this uses the Casimir element. That it took about 10 years to discover this proof. Okay? But this is also something that you learn in the first class. And there's another quote from Hermann Weyl that I really love. So Weyl made an enormous contribution to the representation theory of Lie groups. And he has this quote where he explains why. And he says, the wish to understand what really is the mathematical substance behind the formal apparatus of relativity theory led me to the study of representations of invariants of groups. So Weyl was fascinated by general relativity, and then he wanted to understand what's going on with all these tensors and things like this, and this led him to representation theory. Okay. So now I want to do an extended example of SU2 and SL2, kind of the bread and butter of representation theory. So SU2 is this group. So it's 2 by 2 complex matrices such that A star is identity and determinant 1. So this is matrices of determinant 1 preserving a positive definite Hermitian form on a 2-dimensional vector space. And with a little work in compact Lie groups, you see that this is actually, if you take the quaternions, this is a 4-dimensional vector space, and you take the unit quaternions inside that, so now we get a 3-sphere, and this is precisely what this group is. And we can complexify the Lie algebra of SU2, and what we get is SL2C, this Lie algebra of 2 by 2 complex traceless matrices. So this is from a friend of mine. They wrote to me just when I was preparing this lecture saying, I don't think it is the representations themselves but the groups that fascinates my friend. I find SU2, SLN, SL2, SN, etc. amazing and beautiful animals, but will probably never really understand them. I might someday understand the linear shadows though. So in representation theory we're studying the linear shadows of groups. So SU2, it's a group of matrices, so it has a natural representation. Yeah? It's acting on this space. And I want to call this basis vector y and this basis vector x. And so now what we can do is just consider symmetric polynomials. So polynomials in x and y of degree m. And we get this vector space. And this vector space is an irreducible representation of SU2. And all irreducible representations are of this form. So there's one representation of every dimension, and it's precisely given by this. And this representation is enormously important in, for example, spherical harmonics, the analog of Fourier series on the sphere, and also in quantum mechanics. It's a very incredibly fundamental basic object. And so if you want to write down the matrices here for SU2, so you can work them out, but you get rather complicated matrix entries, and these are basically spherical harmonics. But what we do is we kind of differentiate and look at the action of the Lie algebra. Okay? And that's what I'll do now. So before I was kind of motivating representation theory as being a linearization of what we're acting on. But when we have a Lie group, we can also linearize where we're coming from too. And so we have an algebraic problem, the source and the target. So when we differentiate, we get a representation of this, of SL2. And so I'll just give, this action is very, very simple. So the action of SU2 as these matrices is rather complicated. But when we pass to the Lie algebra, it has a very, very simple, beautiful description. And this is what I'll describe now. So here I have a 6-dimensional vector space, and I want to describe 3 matrices, namely how each of these elements act. And in principle, I should just write down a big 6x6 matrix for each of these guys. But it turns out that they act in a rather simple fashion. So what they do is that each one of these guys is sent to a multiple of another one or 0. And so I can just indicate this. So these are called weight vectors. And H acts as a big diagonal matrix. It multiplies this guy by 5, this guy by 3, this guy by 1, etc. And you see the pattern. And E and F act as so-called raising and lowering operators. So this sends this guy to 5 times this one, etc. So these matrices are very, very simple, basically. Okay. So here we can do everything by hand. We can just write down all of the irreducible representations by hand. There's a passage to go back up to SU2. We can just write everything down. But that's kind of ceases to be possible the moment you're not SU2. And so we would like a more conceptual way of understanding what's going on here. And this is this theory of VERMA modules. So VERMA modules are extremely fundamental objects, and they initially arose in just trying to understand the finite dimensional representations of complex semi-simple Lie algebras. So for SL2C, they depend on a single parameter, and as vector spaces, they're just countably infinite kind of in one direction. So they have a basis indexed by non-negative integers. So here I've just written down what the VERMA module is. Okay, so this goes off to infinity. I have operators that go down, 1, 2, 3, 4, 5, and then operators that take me back up. And you'll notice that this module depends on this single parameter lambda. Okay. And it's not difficult to check the relations and to see that this is indeed a module. And you have to take my word for it, but for other more complicated groups, you can essentially do the same thing. You can write down something very explicit. The VERMA module is a very explicit object. So one very important thing to notice here is that these F and E operators allow you to kind of move around in your module. So if I'm anywhere, I can always go down with the F operators. And the E operators, I can always go up. But the only problem might be that one of these is 0. If one of these is 0, then I'm kind of stuck here and I can never go up. So if lambda is not a non-negative integer, then this module is simple. And so it's a kind of, it's like an element, just indexed by something that is not a non-negative integer. Yep. Whereas if lambda is a non-negative integer, then there's this submodule, which is on this slide. Okay? So here, in this green bit, no matter how I move around, because of this 0 here, I can't get out of this green bit. And so this is a submodule. And then I can take the quotient, and what I get is precisely one of these finite dimensional things I wrote down before. And so in this particular case, this VERMA module looks like a molecule. It's not semi-simple, so it has 2 pieces. So this is big and infinite dimensional. This is infinite dimensional down here. And then it has this finite dimensional thing on top. Okay. So these are the structure of our molecules given by these VERMA modules in this case. So what we see here is that there's a single family of representations for SL2 depending on a single parameter that produce all simple finite dimensional representations. And we get some new infinite dimensional simple representations. Okay? So if you're familiar with discrete series representations, basically some of these infinite dimensional representations are related to discrete series representations. And also we see this rather interesting phenomenon that as our parameter varies, something unexpected can happen. So for example, you might be wandering around close to 3 and you're always simple, but the moment you hit 3, it's not simple anymore. So the KAZHDAN-LUSZTIG conjecture is about the structure of these molecules. So I need to introduce a little bit of technology from representation theory. So we take a complex semi-simple Lie algebra, for example SL2, we take a Cartan subalgebra, a maximally commutative semi-simple subalgebra, and we consider the WEYL group, which acts on this subalgebra as a reflection group. So in our example of SL2, H is spanned by this element H. So this is the typical example. We take n by n matrices of trace 0, we consider the diagonal matrices inside it, and then the WEYL group acts on diagonal matrices by permuting them around. And a very important theme in representation theory is that we think about this finite group as being the skeleton of G. So you think about G as being something like W plus some meat or something. Yeah? And what we would like to do is understand questions about G in terms of this WEYL group. So if you think about something like E8, this is like a 248-dimensional rather complicated object, whereas this WEYL group is an 8-dimensional thing, which is much simpler. So just as before, to any element of the dual in the dual of the Cartan, so-called weight, we get a VERMA module, and it has a unique simple quotient, L lambda. So we saw this before in SL2, namely, when lambda was not a non-negative integer, then we get a simple infinite dimensional representation. When lambda is a non-negative integer, then we get a finite dimensional representation. So the basic problem is to describe the structure of this molecule delta of lambda, which simple modules occur with which multiplicities. So this is the KAZHDAN-LUSZTIG conjecture. So it basically says that the structure of this guy is determined by certain inductively defined polynomials called KAZHDAN-LUSZTIG polynomials. So this is some big molecule, these are the elements inside the molecule, and their multiplicities are given by some polynomial. And this polynomial, one of the reasons that people were initially so excited about this conjecture is that this polynomial indeed depends on the WEYL group, but I'll explain that in a second. So this conjecture was really a new paradigm in representation theory. So if you consider, for example, if you consider the theory of Fourier series, so this is related to, it's about periodic functions, and it's essentially related to the group S1. And if you think about spherical harmonics, this is related to the compact Lie group SO3. And then WEYL developed this beautiful theory, which is essentially the analog of Fourier series for compact Lie groups. But then once you go beyond compact Lie groups, the situation becomes enormously complicated. And this is Harishandra's theory that he developed after the Second World War. And somehow these questions about infinite dimensional representations of Lie algebras are very related to Harishandra's theory. And so essentially this is why we're studying, why people were so interested in this question, because it was extremely relevant to questions in the representation theory of non-compact Lie groups, like SL2R or something like this. Okay. And yeah. So these P lambda mu only depend on the WEYL group. So there's some expression here. You can rewrite this to only depend on the WEYL group in a way that I won't explain precisely. I just want to give you an example of these polynomials. So in this particular case, so this is in fact a picture of an affine WEYL group. So this would be the WEYL group of SL3. So here we see the symmetries of a triangle. But what I've added is a whole lot of translations. And I'm doing this for two reasons. The first one is that it's a two-dimensional object, and so I can draw a nice picture. If I wanted to draw KAZHDAN-LUSZTIG polynomials for a finite WEYL group, I would have to draw something 8-dimensional or something, which I cannot. And the other reason is that these polynomials get complicated rather quickly, and so you can see it in a picture. So there's some inductive method for displaying these polynomials. So So basically, I'm not telling you the rule, but there's some simple combinatorics based on this diagram for generating these polynomials. Do they go one more? Okay. And what you should think roughly is that here we have some big molecule, and each of these triangles is indicating how often some simple representation, some element occurs in this molecule. So we take these are polynomials, we specialize them at 1, and then their specializations at 1 tell us how often this simple module is occurring in a VERMA module. Okay? And as you go out, these get more and more complicated, and it's completely remarkable. So this KAZHDAN-LUSZTIG conjecture was made based on a single knowledge in one case where one of these multiplicities was not 1. So in SL2 we saw that the multiplicities are always 1, and then people calculated some example in SL4 where there's many examples where all the multiplicities are 1, but there's one example where they're 2, and people were very surprised by this, and KAZHDAN-LUSZTIG came up with these polynomials and saw that at the same place the same 2 occurs, and so then they made their conjecture based on that. It's kind of remarkable. So these are these polynomials. So there's some inductive combinatorial rule to define them. And lastly, I just want to discuss the Janssen conjecture, which is some analog of the KAZHDAN-LUSZTIG conjecture, and it's very, very beautiful because it takes us back to forms. So I'm trying to emphasize the presence of these forms, and I want to explain a contravariant form and its relevance to this KAZHDAN-LUSZTIG conjecture. And so a very important thing back here in this KAZHDAN-LUSZTIG conjecture is that here what we want to know is how does this module break up into simple modules over here. And so what we expect here are numbers. But what the KAZHDAN-LUSZTIG conjecture is telling us is that you take some polynomial and you take its value at 1, and this is the number that you want. And this is rather surprising. Why do I need to evaluate this polynomial to get a number? And also one thing that was very interesting in the definition of this KAZHDAN-LUSZTIG polynomial is that you cannot define it without first calculating it as a polynomial. So this algorithm does not work if we specialize these v's to 1. So this Janssen conjecture will explain why there's a q. Well, actually, before it was a v, but yeah, q is equal to v. Okay. So remember our VERMA module from earlier. So this very concrete module. So there's a unique form, so this is called the contravariant form, satisfying these simple formulas. So this one says that if I evaluate this guy with itself, I should get 1. This guy basically tells me, this condition basically tells me that the different weight spaces are orthogonal. So this is orthogonal to everything else, and this is orthogonal to this and everything else, etc. That's what this condition tells me, with a little unpacking. And then this formula allows me to work out what it is inductively, starting from the fact that I know that V0 paired with itself is 1. So starting from that, I can use these formulas to calculate my form everywhere. And what I get is the following. So here I'm indicating the pairing of Vi with itself. That's all I need to know. So V0 with itself is 1, V1 with itself is lambda choose 1, V2 with itself is lambda choose 2, etc. Okay. So I hope that you're all, so you know, I mean, so lambda is a parameter, so this means just lambda minus 1, lambda minus I plus 1, all on I factorial. That's what lambda choose I. I should have put this on the slide. Okay. So this is my form. Now we notice something kind of remarkable. One of the things that we notice is that when are all these guys non-zero? They're non-zero precisely when lambda is not a non-negative integer. Okay? Which is precisely the condition that we've seen before. Okay? So that tells us that maybe something interesting is going on. And now if we do another example, so this is precisely the condition for this VERMA module to be irreducible. So in this particular example, the form is non-degenerate precisely when the VERMA module is irreducible. And what Janssen said is that in general we can, so this is not just one module, the module depends on a parameter. And so what we can do is look at the order of vanishing of these guys at a particular value of lambda. So we view these really as being polynomials, and we look at their order of vanishing at a particular point of lambda. So here's an example of lambda equals 2. So as polynomials, these have no lambda minus 2 factor, and these all have a lambda minus 2 factor, and it occurs exactly once. And so we recover via this form exactly the filtration that we were considering earlier. Okay. And what you can do is, so all of these guys have a factor of lambda minus 2. You can divide this out, and what you'll get is a form on this submodule. And it turns out that this form is non-degenerate. It's non-degenerate. So this is what Janssen did. He considered VERMA modules as a family depending on this parameter, H star. And then he defined the Janssen filtration as being the filtration by order of vanishing of this form at lambda. And these subquotients admit non-degenerate forms by essentially dividing by that parameter. And then Janssen conjecture is that these subquotients are semi-simple. It's kind of amazing. So this VERMA module has this incredibly complicated structure, but what it's saying is that you have this well-defined filtration such that each successive subquotient, there's no interaction. Kind of amazing conjecture. So this was in 1979, exactly the same time as the KAZHDAN-LUSZTIG conjecture. So this explains, so before we were asking how often does this simple module occur in a VERMA module, and we were saying it's given by the value at 1 of a polynomial. But now, because this guy has a filtration, we can ask how often does this occur in a layer of this filtration? And so we can produce a polynomial. And the natural thing to guess is that this is what KAZHDAN-LUSZTIG polynomials are. And if you make this conjecture, then it actually implies the KAZHDAN-LUSZTIG conjecture. So this kind of much more innocent looking statement is in fact equivalent to implies the KAZHDAN-LUSZTIG conjecture. And it's a remarkable instance of hidden semi-simplicity. There's kind of no reason why these subquotients should be semi-simple, but they seem to be. So I'm nearly at the end of this first lecture. So there's one very important thing to mention, which is that in the representation theory of real Lie groups, an extremely important question is to ask, when is a representation unitary? When does it have a Hermitian form? And these ideas around the Janssen conjecture have been extremely important in tackling this problem. So I just want to explain some history, and then I'll give more detail in the next lecture. So we have the KAZHDAN-LUSZTIG conjecture, which is that this multiplicity is the value at 1 of this KAZHDAN-LUSZTIG polynomial. And this was proved 1 year after the conjecture was made. And I think everyone was completely shocked by how fast this was proved. So it used techniques that had been developed about a year before. And very, very sophisticated techniques that had just been developed in order to solve this. And this was done by Brzezinski, Kashiwara, and Beilinson-Bernstein. And the Janssen conjecture, that this graded multiplicity is given by the KAZHDAN-LUSZTIG polynomial. This is Beilinson-Bernstein in about 10 years later. So basically, this Janssen conjecture has kind of repeatedly shown itself to be harder than this one. And then we established algebraic proofs of these. So the algebraic proof of the KAZHDAN-LUSZTIG conjecture was obtained with Ben Elias in 2014, following some highly influential ideas of Wolfgang Zergel in 1990. And then the Janssen conjecture I did in 2016, following some earlier work of Zergel and Kubel. But somehow, the reason I'm saying this is that this guy is kind of more of a complete conjecture than this one. And so when we obtained this proof, we were kind of very keen to see whether we could also get this Janssen conjecture. So the geometric proofs, I'll explain in very, very broad outline how they go in the next lecture. So that they use kind of D modules, perverse sheaves, weights. So these are some of the most sophisticated tools of the 20th century mathematics. Yeah. So it's an absolutely extraordinary story. Whereas the algebraic proofs are rather simple. They use geometric structures, so certain invariant forms, and we have. So in some sense, they're analogous to this original proof of MASCHKE'S theorem, that in order to show some kind of semi-simplicity, you introduce more geometric structure, and then you very, very carefully analyze how that geometric structure behaves. There's an important difference here in that things are not definite anymore. So you need to work with signature of forms, and that makes things much more complicated. But the basic structure is quite similar to the proof of MASCHKE'S theorem. So I will stop here, and thank you, and we'll continue then. Yep. Thank you very much.